Let us start. Good morning, good morning. Good morning, good morning. स्क्रीन शेयर हो रही है?
Yes, sir.
Yes, sir.
Yes, sir.
हमने लास्ट लेक्चर में डेरिवेटिव डिस्कस किया था और उसके वेलोसिटी एक्सेलरेशन एंड सम एग्जांपल बेस्ड ऑन दैट ये हमने डिस्कस किया था लास्ट लेक्चर में. Let us come to the next topic. Next topic is the operations on the वेक्टर फंक्शंस. यानी वेक्टर फंक्शंस के ऊपर डिफरेंट ऑपरेशंस हमने डिफाइन करने हैं और बिफोर डिफाइनिंग द डिफरेंट ऑपरेशंस we should define some scalar functions or vector scalar point field or vector field. That is scalar field, scalar point function. Before scalar point function, we should define the point function only point function. That means a variable quantity whose value at any point in a given region of the space depend upon the position of the point is named as a point function. That means a variable quantity whose value at any point in the region of the space depends upon the position of the point. Yani as per the position of the point, the value of that variable quantity is different. That is named as a variable function. There are basically two types of the point function. Basically, there are two types of point function. Our first one is scalar point function. Scalar point function. Basically, that is a point function which assigns the scalar value. Which assigns the scalar value is called the scalar point function. Let R be a region, R be a region of the space at each point of which a scalar, say phi, is given, then this phi is called, named as scalar point function. Scalar point function, and the R is called a scalar field. Scalar field means what we have for the given region R, each point of the given region R, there is a scalar value is defined for every point of the region R. Then this phi is named as a scalar point function, and the given region R is called the scalar field. And second one is, we can consider the example also. For example, the temperature distribution, the temperature distribution in a medium the distribution of atmospheric pressure in space are examples of scalar point function. Are examples of scalar point function. Now second is, that is vector point function. Vector point function means, as in the above one, in the given region R, if for each point of the given region R there is a vector quantity is assigned for every point, then that quantity is named as a vector point function, and the region is named as a vector field. Let R be a given region of space and at each point of which a vector, that is V, that is depend on x, y, z, is assigned or given. Assigned, or you can say the given, then this V is named as a vector point function, and R is called a vector field. Vector field. each vector v of the field is regarded as a localized vector. Localized vector attached to the corresponding point. Attached to the corresponding point. Yani whatever be the vector is assigned to each point, that means each vector v of the field is regarded as localized vector attached or assigned to the corresponding point. Corresponding point. For example, the velocity of a moving fluid at any instant, the gravitational force are considered as vector point function. Now let us next, these are to be defined, that is vector point function and the scalar point function. Now we define some operations on the vector point function. That is, before the operations we defined a operator. That operator is gradient. First, gradient of a scalar field. Gradient of a scalar field. That means we have given a scalar field. Let for that purpose, let for phi xyz be a function field. K curl phi upon curl z is called the gradient of the scalar field phi and is denoted by gradient of this phi. Therefore, gradient of phi is equal to be I curl phi upon curl x plus j curl phi upon curl y plus k curl phi upon curl z. This will be the gradient. Basically, the phi is a scalar field, or whatever be the operator we have mentioned here, that is curl upon curl x or curl upon curl y, curl upon including I, j, k, that the is also named as a operator. The gradient of scalar field phi is obtained by operating on phi by the vector operator, I curl upon curl x, j curl upon curl y, k curl upon curl z, and this operator, which is denoted by the symbol del, sometimes read as del, sometimes read as a nebula, whatever you want to say, it is del or nebula. Therefore, the gradient of phi will be symbolized, that is del of phi or the nebula of phi. This is the gradient. When this nebula is applied on the scalar field, its name is gradient. Further, we will study when this nebula is applied on the vector field, then what its name. This is a gradient of a scalar field. Now let us consider the geometrical significance or geometrical interpretation of this gradient, what it gives. Geometrical interpretation of gradient. Why we require to find out the gradient of a phi or this nebula of a phi? That means geometrically what it gives. If we consider the surface phi, if a surface phi xyz is equal to c is drawn through any point P, such that at each point of the surface, the function has the same value. Function has the same value as at P. Then such a surface is named as level surface through P. And whatever you can see, let us consider a surface phi xyz is equal to c is drawn through any point P, such that at each point of the surface, the function has the same value. That means function has the same value as at P. जो value P पे है, the same value will be defined in terms of the function at each point of the surface. Then such a surface is named as a level surface. Such a surface is named as a level surface. Let us consider the surface. Let us consider the surface. This surface, that is phi is equal to be C, is the surface where we have a point P. For example, P. For example, if phi xyz represents potential at the point xyz, the equipotential surface phi xyz is equal to C is a level surface. Is a level surface. We consider an example of the potential. If phi represents the potential at any point in the general point, then the equipotential surface will become this phi xyz is equal to not C, is not 0, it is C. through any point, through any point, through any point passes one and only one level surface. That is, moreover, no two level surfaces can intersect. Moreover, no two level surfaces can intersect. We consider like this one. Now consider the level surface. Now we consider the level surface. This we have mentioned above. For complete physical significance, consider the level surface. Through P, at which the function has value phi, and another level surface, another level surface through a neighboring point Q, where the value of the function, the value of the function is phi plus del phi. We consider this as a P from point P, and another level surface this as a from Q. This is phi plus del phi is equal to be C1, and this is phi is equal to be C. We consider these two surfaces. We have already considered two level surface. Moreover, no two level surfaces can intersect. So let R vector and R plus delta R be the position vector, be the position vectors of P and Q respectively. P and Q respectively. Then the vector PQ will become the vector PQ. This is the PQ. Will become delta R. We have already considered that a PQ, that is PQ vector is equal to the OQ vector minus, that means position vector of Q minus position vector of P. OQ means position vector of Q, OP means position vector of P. That is R plus delta R minus R, that is delta R. So vector PQ will be delta R. Now, what would be this del of I, that is gradient of I into delta R, dot product with delta R, because both are vector quantity. Del of I is also vector quantity, del of R. Delta of R is also vector quantity. So their product between those two, either a dot product or the cross product. We consider the dot product here. This is the value of the del of I, value of del of I, dot with value of delta R, that is I delta X plus J delta Y plus K delta Z. This is the value for delta R. Find the dot product of these two. As we have already considered, the dot product of two vectors is just the product of I dot I and J dot J and K dot K, coefficient of I and I, plus coefficient of j and j plus coefficient of k and k. All other will become 0 because of the angle between those two is 90 degree. Only these left behind. The curl phi upon curl x into delta x plus curl phi upon curl y into delta y plus curl phi upon curl z into delta z, which is equal to be symbolized as a del of phi, because we consider here as I dot I is equal to be j dot j is equal to be k dot k is equal to be 1, and I dot j dot k and k dot I all will become 0 because of the angle there, perpendicular angle between 90 degree angle between these two I and j and k and k and I. So what will happen? That means let us consider this as equation number 1. What is that? Is del of phi dot product with delta r. If this Q, the point this Q level surface, if we consider this Q level surface is approaches or coincide to this P level surface, if we consider this Q level, the level surface passing through Q is coincide with the level surface passing through P, then what it means? It means delta phi will become 0. And then in that case, the delta phi will become 0. From the equation 1, the delta phi will become 0. This dot product will become 0. So consider if this Q lies on the same level surface, that means above level surface coincides with the below level surface as P, then del of phi will become 0. Therefore equation 1 reduces to be del of phi dot product with delta r is equal to be 0. What does it mean? It means the delta r, whenever the dot product of two vectors is equal to 0, it means those two vectors are perpendicular to each other. Therefore, del phi is perpendicular to every delta r lying in the surface, lying in the surface. Hence, what concludes? It concludes that the del phi is the normal to the surface, is the normal to the surface phi x, y, z is equal to be c. This will become the normal to the surface. This is the main, it means the gradient of phi gives the normal to that surface, gives us the normal to that surface. And one more thing can concluded from del of phi is what? Let del of phi, any vector is equal to the magnitude of that vector into the unit vector in the direction of that vector. So we consider the del of phi is equal to be magnitude of del phi into unit vector in the direction of this del of phi, where n is a unit vector normal to the surface, normal to the surface, for that let PA is equal to be del n. What about A? We consider A on this one as it is, that is normal. we consider as a normal to the surface is like this one. This is A, unit vector n. This is normal vector, unit vector n. We consider PA on the another surface, that is this is A, and PA consider as a delta n. Consider PA is equal to be delta n, be the perpendicular distance between the two level surface, be the perpendicular distance between the two level surfaces through P and Q, through P and Q. We consider two level surfaces, one is through P, another is through Q. We consider PA is the perpendicular distance between the two level surfaces, that is delta n. Then the rate of change of phi in the direction of normal to the surface, normal to the surface through P is what? That is equal to be curl phi upon curl n. And what is equal to be? It is equal to be limit delta n tends to 0. It is delta phi upon delta n. And what will be the value of delta n? Delta phi n tends to 0. Value for delta phi is del phi dot delta r, and which is equal to be limit delta n tends to 0, because del phi, value of del phi is this one. The value of del phi is magnitude of del phi into unit vector n. That value substitute here. That is magnitude of del phi into vector n dot product with vector delta r divided by delta n. As we know, because dot product of unit vector n into and delta r is equal to be n delta r in cosine of angle between those two, cosine of angle between those two, because n is a unit vector, so its magnitude is 1. So only we have delta r magnitude into cos of theta, and which is equal to be delta n, which is equal to be delta n as per the delta n upon delta r, that is cos theta, angle between the by defining the cosine of theta, that is base upon hypotenuse, base upon hypotenuse. So value of this delta n is equal to be magnitude of delta r into cos theta. Therefore, what will happen in the above one? In above one, this implies curl phi upon curl n will become, that is, this is equal to be delta n, this complete is just one, this n dot delta r will become the delta n, that delta n cancel with this delta n, only left behind the gradient of phi, that is gradient of phi magnitude, gradient of phi magnitude. Hence what it concludes, hence the gradient of phi, gradient of a scalar field phi is a vector normal to the surface phi is equal to be C and has magnitude equal to the rate of change of phi along its normal, because del n is the normal. This is curl of phi divided by curl of n is equal to be magnitude of this del of phi. What does it mean? It means its magnitude is equal to the rate of change of phi along its normal. This is the complete physical significance of the gradient of phi. Means gradient of phi of a scalar field phi is a vector normal to the surface, which we have already considered. This is phi is a hence normal to the surface, del phi is a normal to the surface. And second point, for the magnitude, its magnitude is equal to the rate of change of phi along its normal. This completes about the physical significance of the gradient of a scalar point function, or you can say the del of phi, where phi is a scalar point function. Next, we have a one important topic, that is a directional derivative. Directional derivative. Next topic we consider as a directional derivative. What it states that as per the previous level surface, we consider the same level surface. Let PQ is equal to be delta R. PQ is equal to be delta R. Then limit delta R tends to 0. Del of phi divided by del of R is equal to be curl of phi is divided by curl of R is called the directional derivative of phi at P in the direction PQ. And if we have given this PQ is equal to be delta R, we consider as a magnitude. Then this limit, that means the rate of change of phi with respect to the R, is called the directional derivative of phi at point P in the direction of PQ. It means the rate of change, the partial derivative will give the normal to the surface, that means perpendicular to the surface. It means the directional derivative gives us the normal, not normal, that is tangent to the surface, tangent to the surface. The direction is called the directional derivative of phi at P in the direction of PQ. This is the definition for the directional derivative. Now, how to evaluate this directional derivative? This is the definition. Now, question is how to evaluate the directional derivative of a surface in the direction of some vector. Let n dash be a unit vector, in the direction of PQ. Then what will be the delta R? Delta R will become the delta n divided by cos of theta, because cos theta is based upon hypotenuse. Using that part, we consider the delta R is equal to be delta n upon cos of theta, and cos of theta is equal to be, that is just the angle between the two normals. One is n, another is n dash. This is the angle between the these two, that is cos of theta is equal to be simply this one, dot product of these two. Therefore, what it becomes, curl phi upon curl r is equal to be limit del r tends to be 0 and del r, it will become n dot n dash into del phi upon del n, that is simply is equal to be n dot n dash into curl phi upon curl n, curl phi upon curl n, and which is equal to be, as we have already considered, the curl phi upon curl n is magnitude of del phi, that is n dot n phi del phi magnitude of because n cap is the unit vector in the direction of del phi, and this is the magnitude. A vector is equal to be their magnitude into dot product of the simply product with the unit vector in that direction. So this implies it is equal to be n dash dot with del of phi. Thus, this is the directional derivative. This is the calculation of the directional derivative. Thus, what we conclude, thus the directional derivative that is curl phi upon curl r is the resolved part of del phi in the direction of unit vector n cap. Thus, the directional derivative, that is curl phi upon curl r, is the resolved part of del phi in the direction of del. Since curl phi upon curl r will become this one, which is equal to be apply the dot product of two vectors, because magnitude of this n cap is 1, so it is this equal to be this one, and which is always equal less than equal to be magnitude of del phi, because cos of theta always less than equal to be 1. Cos of theta always less than equal to 1, magnitude of cos of theta. I think simply cos theta is less than equal to 1. What it's conclude, therefore, del of phi gives the maximum rate of change of phi, and the magnitude of this maximum is nothing else, it is magnitude of del of phi. Therefore, what does it give? Del phi gives the maximum rate of change of phi, You can, it is a upper limit, because this rate of change of this is always less than equal to the magnitude of this del phi, and the magnitude of this maximum is del phi. जो maximum value होगी वो इसकी del phi होगी. Hence what it concludes, hence the directional derivative of a scalar field phi at a point, journal point, in the direction of a unit vector A is given by del of phi dot product with A vector. This is the directional derivative calculation way for the directional derivative of a scalar field phi at the given point x, y, z in the direction of a unit vector. This is equal to b del of phi dot with a unit vector in which direction the directional derivative is to be obtained. This is the calculation way to find out the directional derivative. If we have given the in which direction directional derivative is to be evaluated, for that part first we have to obtain the unit vector in that direction, that is A. Unit vector in that direction, that is A. Next we consider some properties of the gradient. Properties of gradient. Gradient means the del operator applied on the scalar point function. That means the gradient. First property is if phi is a constant scalar point function, then gradient of phi will become 0. Gradient of phi will become 0 vector, because this gradient is a differential operator and differentiation of a constant function is 0. So gradient of a constant scalar point function is also 0. Second is if phi 1 and phi 2 are two scalar point function, then following will be holds. First is, that is gradient of phi 1, either we have a plus sign or we have a minus sign, and it will get the gradient of phi 1 plus, either we have a plus or minus, is equal to the gradient of phi 2. Similarly, second one, that is if some constant scalar constant is to be multiplied with the phi 1 and another constant is multiplied with the phi 2, then linearity property also holds, that is C1 times of the gradient of phi 1 plus C2 times of the gradient of phi 2, where C1, C2 are the constants. Where C1, C2 are constants. Third one is, that is gradient applied on the product of two scalar point functions, that is simply apply the rule of the derivative on the product of two functions, that is phi 1 gradient of phi 2 plus phi 2 into gradient of phi 1. And next is a gradient applied on the quotient functions. the rule will be applicable as of the derivative, that is phi2 whole square. Phi2 as it is gradient of phi1 minus phi1 as it is gradient of phi2, provided phi2 not equal to 0. These are the basically 4 properties of the gradient. These are the 4 property of the gradient. Or you can say the, now let us consider the example. Find the gradient of phi, where phi is equal to be three x square y minus y cube z square at the point 1 minus 2 minus 1. What is the question? Question is find the gradient at this point where phi will become this one. Where phi will become this one. Let us do the solution for it. Solution is simple. That is gradient of phi is become this del operator applied on the phi. Three x square y minus y cube z square applied on this for each part. It is I, this with respect to x of this, then with respect to y of this, then with respect to z of this whole part. Consider one by one. That is with respect to x will become g, only with respect to x, that is 6x y, and with respect to y we get 3x square minus 3y square z, and with respect to z is minus 2y cube z. Now this is the gradient of phi, but our aim is to find the gradient of phi at a particular point. So at the point 1 minus 2 minus 1, 1 minus 2 minus 1, that is replace x with 1, y with minus 2, z with minus 1. So 6 into minus 2, that is minus 12i, j 3 into 1, minus 2 whole square 4, 4 3s are 12, into minus 1 it will become plus, that it becomes the minus 9j, and then y is minus 2 whole cube, again it will become the minus, and then z is again minus, so we got the three times of the minus, it will be minus, and 16 k at point 1 minus 2 and minus 1. This is the gradient of phi which is to be determined, जो कि हमें निकालना था. Now let us consider one more example which is of the different type. If we have the vector r is a general vector, that is xi plus yj plus zk, then prove that first part is the gradient of r. This is r is not a vector, this is scalar quantity, that is magnitude of the r mentioned above as a vector is equal to be vector r divided by r itself. Second one is gradient of 1 by r is equal to be minus vector r divided by r cube. And third one is, that is gradient of r raised to the power n is equal to be n r raised to power n minus 2 into vector r. And fourth one is, that is gradient of a dot r is equal to be vector A itself, where vector A is a constant vector, is a constant vector. These four is to be proved one by one. Let us consider the solution. First, we find the vector gradient of R, or simply derivative of this R with respect to X and Y, Z. Then we consider one by one. We have given vector simply R is equal to the magnitude of this R, that is equal to the square root of X square plus Y square plus Z square. This implies simply R square is equal to the X square plus Y square plus Z square. So differentiating partially, with respect to X, we get, that is 2R into curl R upon curl X is equal to be 2X only. This implies curl R upon curl X is equal to be X upon R. Similarly, if we differentiate with respect to Y and with respect to Z, we will get similarly curl R upon curl Y will become Y upon R, and curl R upon curl Z will become Z upon R. In the same way, we would differentiate this R square, value of R square with respect to Y and with respect to Z partially. We will get these two values. Now consider the first part, that is to be determined gradient of R. That is gradient of R, del of R. The value of del is this one, Y with respect to Z, and R simply just with R of everywhere. Substituting all these values we have determined above, that is curl R upon curl X, curl R upon curl Y, and curl R upon curl Z. All these values we have determined above. That is equal to be I into X upon R, J into Y upon R, K into Z upon R. That is R considered as LCM. So what is in numerator? In numerator we have Xi plus Yj plus Zk, which is equal to be vector R divided by R. Hence the result of the first part. Now come to the result of the second part, that is gradient of 1 by R. Gradient of 1 by R. That is equal to be as the derivative of any simple derivative of, or the partial derivative of 1 by f of x, that is equal to be minus 1 upon f of x whole square into simply derivative of and partial derivative of f of x. Using this rule, we can apply here. That means gradient of 1 upon R, that means equal to be I curl upon curl X plus J curl upon curl Y plus K curl upon curl Z of 1 by R. Each one consider as separately derivative of 1 by R with respect to X, with derivative of 1 by R with respect to Y, and then it is equal to be I into minus 1 upon R square into curl R upon curl X plus J minus 1 upon R square into curl R upon curl Y plus K minus 1 upon R square curl R upon curl Z, using this rule. which we have mentioned here. This rule will be applicable for each one, that is with respect to x, with respect to y, and with respect to z. First derivative of 1 by r, that is minus 1 by r square, then derivative of simply r with respect to x or with respect to y and with respect to z. That means gradient of 1 by r. We have already determined the curl r upon curl x, curl r upon curl y, and curl r upon curl z. Substitute their values and consider the LCM. Our LCM will be, and first you consider the values of this I minus 1 upon r square into x upon r, j minus 1 upon r square into y upon r, k minus 1 upon r square into z upon r. Then consider minus 1 upon r cube as a LCM, and remaining will be xi plus yj plus zk, which is equal to the vector r. Hence the result, that is minus times of the vector r divided by r cube. This is to be true. That is gradient of 1 by r is equal to be minus times of the vector r divided by r cube. Similarly, let us consider the third part in the like this one, that is gradient of r ki power n. Using the same rule as we have mentioned above, that is derivative of 1 by, or simply not 1 by, that is r ki power n. Consider the derivative with respect to x, that is n r ki power n minus 1 into curl r upon curl x. Similarly with respect to y, with respect to z, and with respect to z. And that is equal to be I curl upon curl x, j curl upon curl y, k curl upon curl z of r ki power n, which is equal to be derivative with respect to n as per the above rule, that is n r ki power n minus 1 into curl r upon curl x. Similarly, second one, then substitute their values. Curl r upon curl x is equal to x by r, curl r upon curl y is y by r, z by r. And what will happen? That is I into n r ki power n minus 1 into x by r, j n into r ki power n minus 1 into y by r, k n r ki power n minus 1 into z by r. Just simplify, you will get n r ki power n minus 2 as a common, and remaining will be xi plus yj plus zk, which is equal to the vector r. Hence our result, n r ki power n minus 2 into vector r of gradient of r ki power n. This is the result of the third part. Now come to the result of the fourth part. In the fourth part, we have given a vector, constant vector a. Let us consider the constant vector a is equal to the a1i plus a2j plus a3k, where a1, a2, a3 are constants, and their derivative will become 0. Therefore, a dot r, dot product of these two will become a1x, a2y, a3z. This is the dot product of these two vectors. Now our aim is to determining gradient of a dot r, because a dot r will become a scalar quantity. So applied del on this one will become the gradient. I curl upon curl x, j curl upon curl y, plus k curl upon curl z into a1x, a2y, a3z. Simply applied on each one. Simply applied on each one with respect to x, with respect to y, then with respect to z of complete part. So you will get only the value of, that is I with respect to x is only a1, j with respect to y is only a2, k with respect to z is only a3. Other remaining will become 0. Remaining part will become 0. So what is it equal to be? a1i, a2j, a3k, which is equal to be vector a. This is the result which is to be proved. This is the result which is required to be proved. इस तरह से आप इस रिजल्ट को प्रूव कर सकते थे. ठीक है. फॉर एग्जांपल ले ले डायरेक्शनल डेरिवेटिव के.
Yes, sir.
ठीक.
No, sir.
No, sir.
नहीं.
सर
No,
3
sir.
घंटे लगातार
सर
क्लास
बहुत है सर आज के
प्लीज
लिए।
सर.
Yes, sir. 3 hours
बस
हो गए लगातार.
क्या थक गए?
यस सर.
हाँ सर,
अच्छा.
फिर से सर 1 बजे से लेक्चर है.
आपने तो बैठ के मतलब सुनना ही है या सोना है? जो बोल रहा है उसके लिए देखो ना आप. चलो.
सर 3 घंटे से सर एक ही जगह बैठे हुए सर, वो भी तो.
एक ही जगह बैठे हैं.
यस सर.
चलो ठीक. ठीक है फिर. ठीक है भाई. ओके ओके.
थैंक यू सर.